I have a lot of very exciting material here. I had to try to trim it a lot, and I know I also will have a lot of questions, so it's impossible to fit all the very great stuff I have to share in 50 minutes. So I will be around later as well. Make sure you find me. We can have all the discussions you want, because like I love coming to these events, especially for the kind of feedback. Like I love discussing this with peers. And now speaking of peers, just not so long ago, I actually made lots of friends in these events because I work on many of the open source projects in the JVM world. I'm very interested in performance, and I love contributing to other projects or receiving contributions to projects. And so during these meetings, like one of these friends, his name is Alex. We were contributing to each other's projects a lot, like exchanging ideas to have like a very high performance solutions on the JVM, working on caching technologies. And well, at some point he changed the job, so he was not contributing to Hibernate anymore or to Hcache anymore, and he went to work for Shopify. And so we met again at some events. And he has this super interesting feedback about Shopify. Like they are, he's happy because he has a super high performance infrastructure to manage. Like he's some kind of technical lead in there. They have a very high load. And so I'm asking him, oh, well, you will be learning a lot about how to tune Java, how to do even better database access or caching. And he's like, oh, yeah, sadly, yeah, I know all this stuff for the JVM, but we can't use Java here. This is all Ruby on Rails. And I'm like completely shocked because he's telling me that they are willing to invest millions to get Ruby faster because they have a very huge business case to make their infrastructure very efficient. Like there is a very serious amount of money to be made, and they're spending a lot of money in cloud technologies. So I'm like, well, why are you using Ruby? Everybody knows that if your performance is really important for you, you should move to the JVM. But he's like, yeah, but the JVM has a Warmup problem. And I was like, well, we all know about Warmup. What is so special about your situation, right? So let's talk a little bit about like Warmup. You're all kind of experienced developers here. I think you all have heard probably that if you start an application in Java right away and you measure its performance, it's not going to be super great right away because you need to warm it up, right? While other technologies like Ruby on Rails running on its basic interpreted mode, it just starts performing right away. It will never achieve the same performance as the JVM, right? So at a very high level, the performance is going to look something like this, right? So you have your application, which is having, in Java, it starts slowish, and you need to explicitly warm it up. Like you need to have it get a little bit of load so that the runtime starts to learn what am I supposed to do, like which are the hotspots, which is the code that's more likely to be invoked here, while the other applications will just perform okay, and they don't have the overhead of needing to watch and monitor everything that's going on, and so they have a performance advantage over there. Now, of course, after some minutes, the JVM takes over, and that's why we like Java, right? Because it can get you like a very good performance per dollar. If we're talking about clouds, it's becoming more and more important to think like what's your total energy consumption of all these machines you're running, of all these containers that you're running. And another aspect is like how much memory you're paying for all of these things. And another problem there is like the JVM really is quite large. So even if you run like a simple service, it's it starts by having like, well, half a gigabyte at least. That's the baseline starting point for a small service. Now the problem here is like really, it takes, let's say, about 10 minutes after average load for an application to take over, and then to be a good choice for your system. But what if you do continuous delivery, like properly, and you have like a large team who's like pushing all the time, like you have at Shopify? Now it turns out they're deploying in production directly from any commit. Like there is no intermediate QA or staging platform. They have like a proper continuous delivery thing. They have gates and checks and canaries, but then it's pushed in production on average every 5 to 7 minutes. You never reach the full performance. Performance on their use case is going to look like something like this. Now, if you revert this graph and think that these are your costs, well, it's clear that you really cannot use Java in this system, even though you want the best performing application, because it just doesn't work at the performance you need, and there are other runtimes that just will perform better in your specific conditions. Now, this was kind of mind-blowing to me. Like, as a Java person, I was like, oh, wow, I understand continuous delivery is like pretty good, but this is a problem. Now, little bit simple, similar thing. We all have, we work in IT. You probably had nightmares of like Black Friday is coming, right? You will need to be able to scale up your infrastructure a lot, but nobody's going to be able to tell you how much exactly, like what's the load going to be. Well, that depends on marketing. Is your marketing campaign going to be effective? Your marketing and business people, they're going to tell you, oh, we're going to be crazy. It's going to be super awesome. Now, the problem is if you pre-run a lot of JVMs ready to get these, billions of people that want to go to your website, they're going to pay a huge bill for all these servers that are running there, but not really processing much if the expectation isn't reached. And the opposite is also possible. Like, you're trying to scale dynamically depending on the load coming in, but the JVM takes time to start, and then it takes time to warm up. You cannot predict the load as effectively as you would with another system which just starts right away, right? So that's why Lambdas or like simpler services are just way easier to run on a client environment if your load isn't predictable, right? So this starts to be a big problem because we're seeing that Java isn't then a good fit, you're saying, for continuous delivery, or it's not fit if you want to scale elastically, scale on the clouds. So it doesn't fit with trends, people, it doesn't fit with reality. Right? Now, we can go back and have our fun with performance and benchmarks, but if we are not fitting with reality, then maybe we shouldn't use this technology. No, that's a big one. Now, I'm Sanne Grinovero. I work in the middleware engineering for Red Hat, and we do research development in the area there. I'm very focused on the Java aspect, so this was kind of mind-blowing to me, like, oh, well, the JVM is over. Like, it's not a fit for the technology needs of today anymore, unless we can solve these issues, right? Now, I also work on Hibernate primarily, like I've been working on that for 10 years, and I'm leading the team now, and these thoughts that we're having today got me to work with a small core team within Red Hat, which was like the Protean research team, and Protean was the code name for what Quarkus became. So what is this Quarkus? It has this weird tagline. It might sound a bit embarrassing if you're looking for facts and numbers, but supersonic. It's there in the subtitle of the project. Well, what we mean by that is like really that it's designed to fast really fast. But by fast, we mean like really, really fast, like orders of magnitude faster than other technologies that we have seen before on the JVM. Yeah? And we're going to see today how that's made possible. And what are the drawbacks for you? Like, what do you need to take into account of, is this a good platform for you to use? And why is it subatomic? Well, that's another catchy phrase, but we're referring really to the low memory overhead, right? It's, as I mentioned before, like a typical framework will take you, for a small service, you would need at least half a gigabyte of memory, which used to be fine. But now if you're doing microservices and lots of containers, lots of small microservices, half a gigabyte each for a small thing, you're starting to consider, could we write this in something else? It's going to take a tenth of the size, right? Now we want to achieve the same size without having to abandon all the nice tools that we have in the JVM. And we don't want to have any performance drawback. Like, the JVM is great. We want to keep having these advantages. Yeah. So what is Quarkus really? It is a bit in an indefined space. You could say it's a toolkit. It's also a bit of a framework. I hope it will be clearer when we now see some actual demos. Clearly, it's designed to create Java applications. At this point, it's a bit limited to like web development. We are going to expand that, but the focus has been like web applications, REST endpoints, components for microservices. It's very light, and we have been designing it for GraalVM from upfront. Like when we saw what the GraalVM team was doing and we were thinking about this general problem, we were thinking like, oh, there is like so many opportunities here to do something great together. And now GraalVM has some limitations in terms of like, it's not really easy to port your existing application to a GraalVM native image. Now, we are overcoming all those limitations, and we actually love those limitations, because depending how you look at those, the fact that you cannot do certain things, but because it needs to optimize for certain things, they fit perfectly what our goals are with these other projects. So at the high level, what we do is we take your application, which is defined by classes and configuration files, as you're used to, and rather than making a runnable, I don't know, Spring Boot application or a war deployment or an EAR deployment that you then stuck in another application server, we process this at build time, and we create an optimized runnable jar. Now, this optimized runnable jar, then you can do two different things with it. You can either run it on the JVM as is, it's Java jar, start this jar thing, or you can process it again with the GraalVM native compiler, and we're going to produce an ELF binary, so architectural specific little binary, which is pushing the boundaries even further, and we'll see that. Now, the architecture of Quarkus is built around extensions, because we actually need to do some specific magic for different aspects of what we're used to in the Java ecosystem. So, for example, Hibernate will have an extension. So Quarkus has a core thing, and there is a Quarkus extension for Hibernate. And then there is a Quarkus extension for Vertex, and a Quarkus extension for REST-easy, Camel, Netty, Infinispan, and there is a ton more now. This slide, it was like one of the very early launch time. It's been a year since we announced the project. We have hundreds of extensions today contributed by many people. It also has an aim to embrace reactive, both in external APIs, so you can use reactive APIs, or you can use imperative APIs if that's more your cup of tea. Internally, we're making sure that everything is moving to reactive as much as possible, so that you have like zero overhead and extremely good performance. If you are more like into the reactive camp and you need to push the boundaries, if you want to just port applications like you're used to write them, they will just work as is out of the box. They will just benefit from improved performance internally. Now, one of these goals is really like it's designed to be container friendly, which is a new thing for Java, right? First we had Java and we didn't have containers, then containers came along and existing frameworks, they just have to work with it, but they were not really designed for that front. Now, we're aiming here that the application that is built is also actually small on disk. Like all the stuff that we can recognize this is not going to be useful at runtime, it's stripped out. It's not going to be necessary. We're also making sure that the way the dependencies are layered, like we're not Uber jarring everything in one thing, because that makes layering of container images not very effective at all. So we just keep the libraries separate and change it, and your application separate, so you can change your application very quickly and ship just some kilobytes of difference as a delta on top of your existing images and boot it. Now, of course, we want to boot very fast, and we want to consume a lot less memory. Now, when it comes to memory, we need to point out we're not talking about heap sizes. No, that's not the point at all. If your application is running in a container, the Linux kernel is watching it from outside. It doesn't really care how much heap you're using. What it cares is how much residence set memory you're using. So this needs to include all the metadata and overhead that the JVM has on top of the heap, and stacks. So the more processes you have, you will consume some more memory. The garbage collection process will need some memory in its own, and just all the definitions of classes, the metadata of classes, and card tables, all of the nuts and bolts that actually make the JVM, they consume memory that we normally don't see when we're profiling application. We're trying to take into account all this like black matter as well and minimize for that. So when we're measuring memory, this is how we suggest doing it. This is, well, on Linux or Mac, I think it works as well. You just need to put the process ID here, and it will dump you something like this is in bytes and in, sorry, kilobytes. And now this is the total memory consumption of the process. It's not the heap, right? This is typically far larger. So now you can constrain the total memory. There are some new flags here, and I have put a link here to a blog from Christine Flad, who's like one of our colleagues at Red Hat. She's like super deep into how garbage collectors work. She's the designer of the Shenandoah garbage collector. And they added some flags in JVM to allow you to better control like Java running in a container and explicitly bound not only the heap but also like the full process memory. Because what happens when you are not thinking about it? Well, the kernel will see, like if you're running like a Kubernetes or OpenShift, if you're going above the threshold that you allocated, your process is killed, right? And then, okay, well, it will restart it, but you're back again in the warm-up problem, and your service wasn't available for a while. So how do we compare? Now, if I build a small REST service, and by REST I mean we're going to use REST-easy and Undertow, and we expose some toy operations, so it's not a very complex application. And then we compile this to GraalVM native. We can run this in a process of 13 megabytes total, right? So that's the heap size, I believe, is like 2 megabytes, and then there is this like 11 megabytes of overhead. Now that's thanks to the GraalVM native image compiler. You can run the same thing on OpenJDK hotspot, on the managed JVM. It will consume 74 megabytes, and this is like compared to like any other best-of-breed stack that you can find. I'm not going to name any specific, but like if you can test most of them, the best of those will consume about twice Quarkus. Now, if you start making a more complex application, let's introduce Hibernate, Transaction Manager, Infinispan for caching, and the JDBC driver, the JDBC connection pool, and we're not talking about toy connection pools, but like Agral is a like very high performance connection pool. So these are production grade components, but running at Quarkus. The total memory consumption of the process in native image is still extremely low compared to what we're used to. And same for JVM, and you can see now. Now to give you a ballpark idea, this 130 megabytes here, this is probably consuming like 20 megabytes of heap, yeah? But it gives you an idea, like you're wasting 110 megabytes in other stuff in the JVM that you normally are not looking at. So watch for it. It's not a small amount in the big picture. And well, startup time. How are we faring with startup time? First off, how we measure this as well. It's not fair to measure what the application itself is logging, because the first timestamp it's taking is after the application actually was able to do anything, but there is the JVM starting before that, right, which is a very large amount of stuff. So what we do, other problem is many frameworks actually initialize some stuff lazily, right? So they will report, oh, and now I'm done starting, and so they measure way after they started, and then they report I'm done way before they actually finished, because there is a lot of lazy stuff happening in the background. And they're telling you, oh, okay, it was just like 2 seconds. Now, that's not how we want to measure things. We want to measure from before the process was created to actually successfully returning the first request, because that's what matters for our business, right? So I have a little script for that, and what it turns out, like on REST in GraalVM native, we can respond from process doesn't exist to actually respond in about 10 milliseconds. And that's a full running, like no lazy loaded services. Now on OpenJDK, it's way longer, like we're talking orders of magnitude difference, but we're still below the single second mark. Yeah? So it's much more suitable to scale this dynamically or run it in containers at high speed. Now, there is no other framework at this point that can get closer to like 4 seconds if you do this external measurement. You start introducing more frameworks, like let's do JPA as well. You know, competition skyrockets to like 9 and something seconds, while Quarkus in native can still boot in around 50 milliseconds. This slide is actually out of date. I'm not sure if I should, you know, in out of fairness, fix it, but we can actually boot this in 10 milliseconds as well, even on this very low-powered laptop. What happens in 40 of those milliseconds is we're creating the schema on the database. You know, we're establishing all those connections and doing stuff on the database. So the actual boot of the framework is really still in the same ballpark as the rest. Example. And now on JVM, it's a bit more complex because there actually are a lot of classes to be loaded. So it's still going to be about 2 seconds. Now, yeah, 2 seconds, but on a very underpowered machine, right? So we're measuring here on a single core CPU. And why are we doing that? Well, out of, you know, to be able to compare better different things. Like it's, the amount of cores you have actually influences a lot on how much memory you're consuming. So to make sure we can compare things right, we are doing all metrics on single core, small, limited containers. And you know, in those conditions, you can boot in 2 seconds, the full stack. Show us. I'm going to show you. Now, what I have here. I have this small CRUD demo. It's off? Yes, that's good. Because it's not running. But let me show you the code first. So this is IntelliJ. And this is how a configuration file in Quarkus looks like. So it's a simple properties file. What we need is some JDBC configuration. Of course, we cannot really guess those. And pretty much everything else is guessed or inferred. Like, so you can have additional properties, but that's more like to override what Quarkus is automatically understanding from your application. Because during build, we're actually analyzing everything. Like it's like an X-ray of your application and your dependencies, and from there is some logic that's being triggered. So I also wanted to drop and recreate the schema every time we start and import my new example data set. So my example data set is it's here. We have 3 fruits to be inserted in a database. And then we have a web page, which I'm not going to show you. There is just some, it's just doing, just showing you what's going on, but you know, we are doing the backend here. So we have a JPA entity. Now this is full Hibernate, right? Full unmodified Hibernate latest version. Well, unmodified, of course, we patched it, but now all the patches are in Hibernate. Right? So this is using like a named query. It's a cacheable object. It's, you know, you can use anything you normally do in Hibernate. And it has a name and it has an ID. We also have like a JAX RS REST endpoint mapped with REST easy. So we're going to have like a method to list all the fruits, a method to retrieve one fruit from the database, to create a new fruit and persist it, update it, and delete it. No, CRUD. I also have like a helper thing to print timestamps when I measure for a boot thing. And some more helper. Now, this is all the application. Like there is no need to add additional ceremony because like you wanted a REST endpoint, fine. What do? You inject an entity manager, right? So there is CTI here at place, but CTI isn't going to be running at runtime. Like everything is being processed at build time, and when generating the code that's making this magic work at runtime as you would expect. So now, of course, this is a Maven project. You could use Gradle as well. We are importing some dependencies from Quarkus, and then we are importing, well, the support. You remember this approach via extensions. So we are importing the extension which takes care of Hibernate, which it's transitively pulling in a dependency on Hibernate, right? It's not having a different version of Hibernate. It's just making it easier by having transitive dependencies. And then we want like the connection pool, REST easy, and the JSON-B encoders, the GDBC driver for MariaDB, And smaller I, open APIs, I like to use those. And we have testing support. But let's just run this. Well, first I need to build it. Clean package. Not much magic here going on. It's just Quarkus. Oh, sorry, I forgot to show you. There is a Quarkus plugin here. Quarkus Maven plugin. That's what's doing all the magic. You add that thing, and now what we have here is the jar, which contains those two classes and the resource file that we have, but we also created a runner jar, which you can run like this. Quarkus demo MariaDB, I want a runner version. Start is up, and there it is, up. It started. Let me go back to our web service. Yeah, so now I have those three fruits that we created. A cherry, a banana, and still just an apple there. Let me store a new fruit. Everything is working fine. Now, this is pretty much Quarkus. The difference really is like how it processed all of these things. And it booted in, so here it's reporting a 1.5 seconds, but we're not doing the proper measurement I explained. Like, let me show you though. I have some scripts here, show their RSS, right? So this is consuming now 290 megabytes of memory. Now, of course, because we didn't really constrain the memory at all, right? So the JVM does kind of use ergonomics. Let's stick this in a 30 megabyte heap and see, does it still start? Does it still work? Yes. It didn't even consume far more. Where is my script? Now, of course, you see this is getting quite lower because like heap is there, but there still is some other overhead like this. Now, of course, if you compare this with other frameworks, you would see like a very higher cost. Like this is complete cost of the processing memory. But let me go back to slides because I have far many more things to show you. How does this work? Well, before explaining how this works, let me explain you how Hibernate or other frameworks or like the typical libraries normally boot. Now, what we have is your application, which is like a Java, jar, or maybe a deployment. Now, at boot time, when you're starting this thing, let's say you're booting Hibernate. Like you have many frameworks in your stack, but you're going to boot one by one all of these components. Now, the first thing that we need to do is, well, like I'm a Hibernate guy, so I know all those details there, right? So I'll take this example. But first thing is like, where are the configuration files? Like, I don't know if you're using a persistence XML file or maybe Hibernate or properties or Hibernate HBM file. There are multiple ways that you can configure this thing. I need to search for all of these things. And I need to search them on the file system in various places, and I also need to search them across the resources. Now, we live in a modular world, modular application servers. Searching for resources means I need to actually check different class loaders in different orders. There are rules to respect. So, I'm going to check for the first resource here. I fail over there. I fail again. Exceptions being swallowed. There is a lot of stuff going on there. Now, when I find one, let's say I find a persistence XML. Okay, it's an XML file. Let me boot, the XML parser that the JVM has. Now, that's 300 classes that need to be loaded. They need to be initialized. They have their static constants in there that need to be initialized as well. That's 19 megabytes of memory just in constants, if you measure that. That's not to parse the file. That's just to boot the XML parser. Yeah. And then we can finally parse this thing and create a model, which is our configuration file. And from there is more work to do, right? So at that point, it's like, OK, well, this is the configuration. Where are the entities? And off we go again. Let's find anything that might be annotated with like JPA annotations or Hibernate annotations everywhere in the class path, because I have no idea where you might be hiding those, and you're going to complain if you're not finding them, So scanning. This scanning, if it's not done properly, like in all time, we would do it via reflection, and that would be very slow. And of course, it's depending, the cost of this is depending on how many jars and how large are these files that you're having on ClassPath. Now, we have many of those normally. Right? Now, then we need to find extension points, like, oh, you have this additional plugin or like service or callback factory that you want to be registered with the integration thing that we automatically register and bind to it, right? So that's more ClassPath scanning and searching and thing. Now, finally, we built like this in-memory meta model, and most of the time, exception, oh, you forgot a critical annotation there. Let's start over. Kill it. When you're lucky at this point, we need to create like an optimized version of this model so that then when we're actually working, we have like most of the prepared statements that we will need at runtime. They will need to be ready so that we're not generating too much garbage at runtime. All the injection points need to be created. We will need to create like class definitions for proxies. We might need to enhance your objects, which means like bytecode manipulation of your classes, which also implies like if I'm changing the bytecode of your class, then the class path, we need to get rid of the old definition. We need to drop the class path, create a new class loader, and start over. And then finally, you validate the world. But this was just Hibernate. Then, the next framework starts and says, let me find everything which has another, the JAX-B annotation or the CDI annotation or so on. Now, this is why it takes a long time to boot and why there is a ton of classes being initialized in the JDK, because there is a lot of work happening when your application is starting. And well, finally, eventually, you manage to get, okay, we can open 8080, we can start responding, right? Now, that's quite some work, and it's, it's intensive on the JVM side. It's loading a lot of classes, like this XML parser, these 200 XML parser files, which you only need once to parse the configuration file at the beginning. They have all been loaded and maybe optimized, maybe evaluated for compilation by JIT and all that. Now, that's a lot of fat. When you put this thing in a container and this fat starts to matter, that's one thing. Like you're paying some cost there. What's more worrying is that you're paying this cost many, many times when you go to microservices or continuous delivery, and you're redeploying over and over and over. Every time you're redeploying or scaling up your service, you're paying that cost again. You can put some number in dollars on that cost, like $1, $2, I don't know, depends on your system, but it's one each. Now, in Quarkus, we try to do everything or as much as possible during the build of the application. And it makes a lot of sense if you think of it in terms of containers and cloud environments. In terms of bytecode, so then we take this state and we create via bytecode processing or bytecode generation, we capture the state of what's a working state for your application and dump that to disk so that then this is the state you can go directly into runtime mode. So this is how it looks like. All this, the configuration, the analysis, the scanning thing, we do it via this Maven plugin, right? Or doing the Gradle plugin. Now, the drawback is you're not allowed to make changes after the application is built, right? So forget about the idea of like, I'm packaging my application and then I deploy it on the server and configure, I change the data source from Postgres to Oracle. Like, who would do that anyway? I hope you know which database you're going to target. And we all know that it's not a good idea to change a container image after you shipped it, right? So you're building a container image here, and that's meant to be immutable, and the state you need there is all you have. Like, you're not going to make changes, or you want to maybe build another one. That's entirely possible. Now, the state at the end, that goes directly to load the classes we need for actual running, and only those, and that's up. Let's get the second tool, so the extension model. So these extensions that we have, they take care of helping each of these individual frameworks to accomplish these optimizations. But we can also like physically strip out all the stuff that you don't need. So for example, I had this rant about XML parsers, right? Now, if you need XML parsers because you're parsing configuration here, but you don't need them at runtime, in a Quarkus build application, the XML parsers will not be in the final shipped code. They are not there because they are not really needed, right? Now, the same goes for a lot of other dependencies, like Hibernate does bytecode enhancements of entities. We use ByteBuddy for that, which uses ASM. Now, that's many very cool libraries, but we only need them during the build. They will not be included in your image at the end, which is great for many reasons, right? So you're not going to support those libraries at runtime, and they're not a security liability or anything. So an extension looks like this in terms of Maven models. Like you have a deployment Maven model and a runtime Maven model. Every single extension in Quarkus is modeled like this same pattern. So we can actually separate the code physically, like this is going to be run in this phase and this is going to be run there, but also we're only going to ship the dependencies and the model runtime itself. Gendex is a library we use to find all the annotations. It has many great features. Like the main one is it doesn't initialize the classes at all. Like so it's going to search or give you a way to identify classes which have specific annotations or specific interfaces directly from an index. This index can be pre-built, and it can be stored in your jars if you want. You can do many interesting things, but the most important aspect is we do this once on behalf of all the frameworks that are booting, right? So there is no exponential complexity there. Arc is a new project that we use. It implements most of CDI. It's not a full implementation of CDI at this point yet. It does all the dependency injection, but it does it all at build time. So you have no overhead at runtime. And Gizmo is a bytecode generation library that's helpful to create this state or create these representations of state that are your application. Now, this means like you're loading far less classes, and it's smaller. And the final point is really interesting. Like most of the things that we do at build time are exactly the red flags to compile something in GraalVM native images. Like there are some rules. You cannot do bytecode enhancement. You cannot do proxies. You cannot do reflections unless you specifically list, make the full list of all those things. But we do these all of these things. We are done at build time. They are not done later. They are not even part of the set of code that's being compiled by GraalVM. So they're not a problem at all. We can do this in a far easier way than convert a traditional application to GraalVM. Just general architecture. So we have these basic components, right? The Graal SDK, which we use to give hints to the Graal compiler about what each of these components are needing. And every extension, and lots of people have contributed extensions. You can add your own there. Every extension is driving these basic core components so that, for example, it can let the Graal compiler know about I'm going to need these specific flags or this specific behavior, or I'm going to need annotation scanning and so on. But there is one more consequence here that I have not mentioned yet, and it's really, really nice. We call it developer's joy aspect of Quarkus. And this is a consequence of being so extremely light in booting and also not loading all those classes at all. Let me show you. I'm going to kill the application I started before, and now we're going to run it in a different mode, the development mode. Now, development mode, it's up and running, and it's even opened like the debug port. Now, what does it imply? So first off, it resets my database. You remember we are setting this to import the schema every time, right? Now in development mode, you have the JVM running there, and it's now watching your project for changes. Yeah. Now if I switch to my IDE, and now I can make any change I like, right? So let me add the fruit here. Yeah? So if I add the fruit, Now, easy. I change a resource. Now, let me refresh this. What's happened? You see in the bottom left, hot replace, total time, 360 milliseconds. Now, this was the full reboot of the stack. Why was it that when I start this in JVM mode, it takes 2 seconds, and now it took only 300 milliseconds? Well, because we are not restarting the JDK, and I told you, like, the biggest overhead is all the JDK classes that need to be reinitialized now. Here we have a complete drop of the code of your application. It's completely being rebuilt. All the class enhancement, scanning, everything that we need to do to build your application is being done in those 300 milliseconds, and then is restarted again. Do I have a Mango here? Yes, I have. Yeah. Let me delete some. And now this was easy. I changed the resource, right? But now we're not using agents or like JRebel or anything. Those things, they have been amazing. But there was a difference between restarting your application from scratch and clean and seeing if the agent was able to do some magic for you. Now let's do something which is like a bit more crazy. I could change the entity. Yeah? Now you see there is this find all here. They are sorted by ID. Yeah? So if I go here, Apple Mango, sorry, well I forgot those. Well, let me change the query. Sort by name. Yeah, I save. I go here. I refresh. And there I have A, B, C, M. Well, sorry, M. Oh, yes, I still have the Mango in my import, of course. Don't you believe it changed the code? I can go back and set the ID because it was maybe not too clear. And see, now it's no longer ABC. Yeah, I made the change to the entity, and everything has been rebuilt. So even the meta model of Hibernate has been restarted, and the whole application has been restarted. That's all really because it's very light. There isn't much that needs to be reinitialized or rebooted at all. So that's what we call developer joy. You just change your code while it's running, and you keep going. And I can even make errors. Let me show you one. I lost my screen. Yeah, let's make, I don't know. I forgot the ID here. Yeah? And you get there. Oh, the Hibernate thing, you have no identifier here. We can go back and fix my thing. There we are, application working again. Yeah? It feels a bit like PHP, right? It feels a bit dirty. But that really is the point, right? You might have seen people that, you need something very light. You do it in PHP, and a change is needed. You just SSH to the server, make the change to the page, and you're done, right? It's very dirty, but sometimes it's very effective. So these extensions, you are needing them to bypass the GraalVM limitations, but they also enable you to do all of these optimizations. Yeah, only 5 minutes. So where is the catch? Well, that's the fun part, right? There isn't really. It's consuming less memory, which is just a good thing, right? And you're also having far less code actually loaded in the JVM, which is great because the just-in-time compiler can focus on the code that matters for your runtime and not on all the other garbage which is there. And a lot of optimizations the JVM can do are based on like how many types of this kind there are around. Can I optimize this polymorphic or megamorphic call or not? So the performance is pretty good. And why do I mean like no compromises? Like you're really running here the best of breed of the JVM stacks here. Like they are unmodified or even better in some cases. Now, for example, the HTTP layer is based on Undertow, which was used to win all the benchmarks on what's the name again? I have a lapsus. Tech and Power, like all the Tech and Power benchmarks. Like at some point they were being run and like they were being won by Undertow. That was Undertow 2. Then Vertex took over. Now, fun thing, the Vertex team and the Undertow team, they're working together on the Quarkus REST endpoint. It's going to be the best of breed of those two things. This is work in progress, but it's almost merged already. So that's just an example of like, we are also very focused on like, we want the best runtime performance, and it's not just about the build and things. Unfortunately, I'll have to skip this. But yeah, just to wrap this up. So it's the same good old Java. Like, you have seen this code. How long is it going to take you to learn this? Like, it's the same REST-easy, it's the same Hibernate, and it's the same other 200 frameworks that we are supporting out there. It's just being built and packaged in a different way. Like, there is this notion of application server, which we are getting rid of because of containers and how the classes are working. And now, a note about the native image performance. When it's compiled all the way to native, the performance is slightly lower. Oh, sorry, I didn't show you. I need to show that. It's too good. Let me kill the demo here. So let's build this as a native application. Let me check if I'm running the right JVM here. No. I'm using the Graal version 19.3.1 for JDK 11 now. Let me do a clean package, but enabling the native profile. Now, this is going to do all the same processing that we did before, but then the runner jar, which is generated.
Was that a Maven profile, or was it?
It's a Maven profile, yeah.
Should it not be -p?
Yes, but I trigger it via the environment variable, yeah. But you're right. Typically, it should be -p. Now, this is going to take a couple of minutes. That's why I let it run right away, and then I can finish my talk. But it's also interesting to watch what it is doing. Like, if you see here, now that's the command line that's invoking the native image thing, and you have some statistics here, but in between, now you see, oh, Hibernate core 5410, what? This is the compiler. But it's starting the frameworks in the JVM. Like, the compiler is running in Java. That's how GraalVM works. And it's actually starting our libraries. So that's their libraries, like, we can delegate the work of like building this metadata, validating the model, creating the state that you need at runtime. That's being created within the memory space of the compiler. And then, when we're ready to, like, we have like a booted up Hibernate. The only thing that's missing there is, of course, we didn't do connections to the database, right? We stopped right before that point. Now, when you have that state, now we take a snapshot of the heap, and that's what the native image is then compiling to native code. Right? So the actual booting of the frameworks is completely done. And there is a very nice additional benefit from this. Now, it means that all of this state that's being generated and captured during the boot is a compile time constant. The compiler can go nuts on optimizing additional code based on the assumptions that it's gathering from this output. And by nuts, I mean it can actually remove every single symbol and method or class which is not going to be absolutely necessary at runtime. And that's why the binary is sorry. It's almost done. Let me just finish talking about the native image performance. So it is slightly lower than the JVM mode, at least in our tests. It will depend, of course, on your specific application. Like, generally speaking, we see it is like 30% slower with our typical Quarkus REST endpoints. But still, it is a very winner it's a very good economical choice of technology because it consumes far less memory. If your build is in amount of megabytes, that you're consuming, and most of us are, maybe you're not aware, but all machines on clouds, they are scaling up mostly by memory cost and more than by CPU's cost. And you don't need Warmup. You remember my big problem, like the JVM is not fit for this line of business? Well, now it is. This is a solved problem. This is making it fit to run your applications written in Java, using Java libraries. And you have no warm-up problems, and you can like instantly scale up and down. You can create lambdas with this code. And there is a very nice additional thought, which is you don't really need to make a choice up front about this, right? You can build everything in Java, use the debuggers if the JVM, have fun on the JVM, and then at some point, if you see that the kind of needs you have at runtime are a better fit for the native image, you just compile it in a different way. Let's see if the compilation finished. It's there. So I said this is a binary, so I don't use Java to start it. It's target, and there we have Quarkus demo MariaDB runner, no jar. Yeah, what is this file? It's an ELF Linux binary, and if I press enter, it's up in 17 milliseconds. That was including connecting to the database and creating the schema and everything, right? We can check for that. Where is my browser again? There it is again with the 4 things that we saved, and it's a fully functional application. There is absolutely no difference because the compiler just took the same code we had and created, it packaged it in a different way. Sorry, lost. And that's it. Thank you very much. I have some resources here if you want to check it out.